The decomposition of sulfuryl iodide to sulfur dioxide and iodine gas has a rate constant of 3.8 times 10 to the negative 3 per hour at a temperature of 280 degrees Celsius and an activation energy of 210 kilojoules per mole. Determine the rate constant for this reaction at 380 degrees Celsius. So if you're new to these types of questions, it's a good idea to begin starting out by listing what's known and what you want to find out. Of course, by the time that it comes to writing a test, you want to be able to have done as much practice as possible to the point where you're able to tell right away that, for example, we're going to use the Arrhenius equation for this to answer this question. But whenever you're starting out with something new, this is always a good idea. So, we know that at a temperature of 280 degrees Celsius, we have a rate constant of 3.8 times 10 to the negative 3 per hour. What's unknown? We're looking for a rate constant at a temperature of 380 degrees Celsius. We also know that the reaction activation energy is equal to 210 kilojoules per mole, and we know that activation energies are temperature independent, so they don't depend on the temperature of a reaction, and they're always going to be the same value for the same reaction as long as it follows Arrhenius kinetics, which are going to be the majority of, or pretty much every reaction that you work with in first year general chemistry. We also know that the reaction is first order, given by the units of the rate constant. So we know that if the units are in per hours or the inverse of time, then that's going to be a first order reaction. However, to solve this question, this information isn't necessary for us because the Arrhenius equation works for all orders of reactions. So whenever you have a question where you're given an activation energy, the first thing that comes to my mind, at least, is using the Arrhenius equation, because it's one of the only ones in your first year general chemistry textbook that relates activation energy with temperature and rate constants. So the general form of the Arrhenius equation is K equals A, which is called the pre-exponential factor, multiplied by the exponential of the negative of the activation energy over the gas constant multiplied by temperatures. However, another form that you may see this in is in the modified version of the Arrhenius equation, which looks like this. So it's the ln of K2 over K1 is equal to the negative of the activation energy over the gas constant multiplied by 1 over T2 minus 1 over T1. So why does this work? Well, if we change some stuff around here, For example, if we add the ln of k1 to the right side, we get a linear equation that is easily plottable on a graph. So the ln of k2 is equal to negative EA, activation energy, over the gas constant, multiplied by 1 over T2 minus 1 over T1 plus the ln of K1, which you can see looks similar to y equals mx mx plus b. So the y-intercept, if we plot the ln of k over the inverse of temperature, we get a downward sloping graph where the y-intercept is equal to k1, or the ln of k1. This here is ln of k2. The slope is equivalent to the negative of the activation energy over r, and on the x-axis we have the inverse of the temperature. This is also important because you might get a question where you're given, for example, a question that asks, given the slope, which is or the slope of ln k versus inverse of time graph is equal to a specific value, what is the activation energy? Well, knowing how this graph works, right, that it's a linear equation, you know that the slope is equal to the negative of the activation energy over r. You could solve for that easily. So, getting back to the question, so ln of k2 is equal to negative of the activation energy over the gas constant multiplied by 1 over T2 minus 1 over T1 plus ln of K1. So what is our activation energy? Well, it's 210 kilojoules per mole. However, our gas constant is in units of joules per mole Kelvin. So we want to change our activation energy into units of joules per mole. In fact, most first-year general chemistry questions, you really want to be careful for the units that you're given, because that's where a lot of students make mistakes, and it can ruin your entire solution. So this is equal to negative 210 times 10 to the 3 joules per mole over the gas constant, which is 8.314 joules per mole Kelvin, multiplied by 1 over T2. So our T2 is this here. In fact, we should give them their subscripts. T2 is equal to 380 degrees Celsius. However, we want to get that into units of Kelvin. So when we're working with equations in first-year general chemistry, you always want to change your degrees Celsius into Kelvin. And to do that, you simply add 273. So 380 degrees Celsius is equal to 653 Kelvin, and 280 degrees Celsius is equal to, let me just rewrite this, 280 degrees Celsius is equal to 553 Kelvin. So we plug that into our equation here. 553 kelvins plus the ln of K1, so our first rate constant, which is 3.8 times 10 to the negative 3 per hour. So this is ln of K2. Now, after plugging in all of this into our calculator, we know that the joules per mole cancels, the kelvins cancel, right? Because if we have an inverse in the denominator, that equals a numerator over the inverse of that unit, right? So the kelvins cancel, and we get what's left in units of per hour. So ln of K2 is equal to 1.42135 per hour. And if we solve for K2, we simply take the exponential of the left side. So we take the exponential of this here, 1.42135, and we get that K2 is equal to 4.14 per hour.